SPH4U, force in motion, 2.4 circular motion. So first we should start off with the principles of circular motion. So first one is that the speed or magnitude of the velocity vector is always constant, while the direction of the vector is not constant. And that change in direction means acceleration, and then there's centripetal acceleration which points towards the center of the circle. So there's two types of circles in circular motion. There's a vertical circle and a horizontal circle. I'll explain what a horizontal circle is later. So this is a vertical circle. We can see the entire circle on the xy plane. So if this circle then signifies the path of the circular motion, these arrows, they represent the velocity vectors. So as you can see, they all have the same magnitude but different directions. And these green arrows, that's centripetal acceleration. And centripetal acceleration points towards the center of the circle. So now I'm going to tell you a few of the equations that will be very useful in solving these questions. So acceleration is equal to velocity squared over r radius. Centripetal force is equal to mv squared over r. Velocity is equal to 2 pi r over t time, where Fc is equal to Ft. This is the force of tension in the string or rope that is that has the object on it that's creating this circular motion, plus the force of gravity. So this is an example of a question that uses a vertical circle. So a lock of mass 200 grams is attached to a 0.75 meter long string and is swung in a circular vertical plane. So what is the slowest speed that the lock can travel and still maintain a circular path? So we know this is a vertical plane, so we can use the equations that we learned last slide. So the slowest speed is when the force of tension is equal to 0. So now we can plug this into our equation. So centripetal force is equal to the force of tension plus the force of gravity. So we need the slow speed. This turns out into 0. So Fc is equal to Fg. So mv squared over r is equal to mg. Masses cancel out. So v squared is equal to g times r. Velocity is equal to gr, square root of gr. So velocity is equal to square root of 9.8 times 0.75. So that means that the velocity would come out to be 2.71 meters per second. So now we're moving on to part B. What is the tension in the string at the bottom of the swing? So Fc is equal to Ft minus Fg. So equals Fc plus Fg. So Ft is equal to mv squared over r plus mg. It's Ft minus Fg because Ft is going in the outwards direction while Fg is going in the downwards direction. So this is the center of the circle. So the lock is down here, or the ball. So first the gravity is pointing downwards, but first tension is pointing upwards. Alright, so first tension is equal to mv squared over r plus mg. So force of tension is equal to 0.2 times 2.7 squared 0.75 plus 0.2 times 9.8. So force of tension comes out to be 3.91 newtons. So that's how you would approach a vertical circle question. Period and frequency. So the period is the time seconds required to complete one revolution, and the frequency is the number of revolutions per unit of time. So with these two new definitions, we can actually create some new equations. So the relationship between the period and a frequency is t is equal to 1 over f, and that f is equal to 1 over t. Alright, so we know that the equation for centripetal acceleration is v squared over r, and velocity is equal to 2 pi r. So AC is equal to 2 pi r over t squared over r. So centripetal acceleration is equal to 4 pi squared r over t squared. Then we can also clean our equation. AC is equal to 4 pi squared r times 1 over t squared. Centripetal acceleration is equal to 4 pi squared r f squared. So this one can be used if you have the period. Well, this one can be used if you have the frequency. Alright, so now I'm going to go over a banked curve question, which is also known as a horizontal circle. So a car is driving on a slanted ramp in a curve with a radius of 50 meters. The bank angle is 50 degrees. So what's the ideal speed of the car, i.e. there's no friction? So first, let's draw a free body diagram, which will help explain what a horizontal curve is. So you have an angle of 15 degrees. Then you have this car here. It's acting downwards. The force of gravity, which is always straight down. Force normal going this way. And force normal is going perpendicular to whatever surface it's on, so it's at an angle. So if we zoom in on this car, we have this upwards, so Fn. So here we have Fn cos of theta, so that's the y direction component, Fn sine of theta, which is the x component. So if we draw this out like this is actually a circle, but just in the horizontal plane. So unlike the previous example where it was in the vertical plane, we can't see the full circle, but there's still centripetal acceleration towards the center of the circle. So we will be using that concept to solve for the ideal speed. So we have Fn cos of theta equals to Fg, because that's what we have in the y component of acceleration. So in the y component of motion, sorry. So Fn is equal to Fg cos of theta y. So in the x direction, we know the force net is equal to the force, centripetal force, which is equal to Fn sine of theta. So centripetal force is equal to Fg over cos of theta times sine of theta. So if you recall, cos, sine over cos, that is equal to tan of theta. So we have mv squared over r is equal to mg tan of theta, and masses cancel out. So we have v squared over r is equal to g tan theta. So v is equal to g tan theta r whole square rooted. So the velocity is equal to 50 times 9.8 times tan of 15. So that means that the velocity is equal to 11.4 meters per second. And in questions like this, the direction is typically not needed.